Hi, myself Dr. A. Rushi Kesava, Associate Professor, Department of Mathematics, Marri Laxman Reddy Institute of Technology and Management, Dundigal, Hyderabad. So, last classes we already discussed eigenvalues and eigenvectors, properties of eigenvalues and eigenvectors, Cayley-Hamilton theorem, and find inverse and powers of the matrix by using Cayley-Hamilton theorem. So, in this session, we discussed diagonalization of a matrix. Okay, diagonalization of a matrix. Okay, next. So, the definition of the diagonalization is if a square matrix A of order n has n linearly independent eigenvalues, then there exists an invertible matrix P such that P inverse AP equal to D is a diagonal matrix. Okay, so P is the model matrix, P inverse AP, A is the given matrix, P inverse AP equal to D. D is a diagonal matrix, only diagonal elements on the given matrix. Okay, that is the D. D is the diagonalization and D has the diagonal matrix. So, for example, let A be a square matrix of order 3. Let us take 3 by 3 square matrix. The eigenvalues are the matrix are lambda 1, lambda 2, lambda 3. That is the eigenvalues. And the corresponding eigenvectors are x1 equal to x1 y1 z1, x2 equal to x2 y2 z2, x3 equal to x3 y3 z3 are the three eigenvectors of the given matrix A. Okay. So that is. Then the model matrix written as P equal to x1, x2, x3. That is, write the eigenvectors on column wise. x1, y1, but is x1, y1, z1. That is first eigenvector. x2, y2, z2 are the second eigenvector. x3, y3, z3 are the third eigenvector. So we can write P is x1, x2, x3. That is the eigenvectors of the column wise. We can write the column wise eigenvectors. That is capital X1, X2, X3 are the matrix P. That is the model matrix. Next definition is similarity of a matrix. A square matrix B of order n is called a similar matrix to a square matrix A of order n if B equal to P inverse AP for some non-singular n into n matrix P. The transformation of a matrix A by a non-singular matrix P to B is called a similarity transformation. So, similarity matrix is B is also similar to A. A is a diagonalization matrix, P inverse AP equal to A. P inverse AP equal to D. So, similarity matrix B is similar to A. That is, we can write B equal to P inverse AP. And some more points are the transformation y equal to px. X is a same matrix, column matrix, x1, x2, x3. We can write to capital X is x1, x2, x3. P is the model matrix. That is, we can write eigenvectors x1, x2, x3. So, y equal to px. Y is y1, y2, y3 like this. Okay. So, the matrix y equal to px is called a similar transformation. Okay. And also a matrix is said to be diagonalizable. It is similar to a diagonal matrix also. Okay. And one more important is a n into n matrix is diagonalizable if and only if it has n linearly independent eigenvectors. Okay. That is the n linearly independent eigenvectors. For example, we can take 2 by 2 matrix. Let us take any 2 by 2 matrix. It has 2 linearly independent eigenvectors. Let us take any 3 by 3 matrix. It has 3 linearly independent eigenvectors and so on. N into n matrix, they have n linearly independent eigenvectors. Okay, that is. And also, let us consider capital A is a diagonalizable matrix. Then A is similar to a diagonal matrix D equal to lambda 1, lambda 2, lambda 3. The diagonal elements are lambda 1, lambda 2, lambda 3. Here lambda 1, lambda 2, lambda 3 are the eigenvalues. Okay, eigenvalues of the matrix A. Okay, that is the A is the similar to the diagonal matrix. Now let us consider AP equal to A into x1, x2, x3. That is A is the given matrix, P is a model matrix. That is like the corresponding eigenvectors, column wise eigenvectors of the matrix. That is the P equal to x1, x2, x3. So we can write A equal to A into x1, x2, x3. We can also write A into x1, A into x2, A into x3 also. Okay. Now A is the similar to the diagonal matrix, that is D of lambda 1, lambda 2, lambda 3. It is the similar to the diagonal matrix. So we can write that equal to lambda 1 into x1, lambda 2 into x2, lambda 3 into x3. We can also write in this way x1 into lambda 1, x2 into lambda 2, x3 into lambda 3. Okay. Now we can also write the above form is matrix of x1, x2, x3 and the diagonal values lambda 1, lambda 2, lambda 3. Okay. So we can also written in this way. So finally this matrix is P and the matrix is D. Okay, that is the diagonal matrix. So P into D, that equal to P into D. So AP equal to PD. So finally AP equal to PD. Okay. Yes. So this is the AP equal to PD. We can also write multiplying on both sides P inverse matrix. Okay. Now we can get this one is just write the multiplying above matrix by left side and P inverse, that is P inverse AP equal to here also P inverse PD. So that is also we can written P inverse into P into D. Here P inverse into P is, we know that P inverse into P equal to I, that is the identity matrix. So whenever we can also write P inverse into P into D, that is I into D, that equal to D. I is the identity matrix. We can multiply anyone itself is a matrix with multiplying identity matrix, that is ID equal to D. So finally we get D. So this is the diagonalization form. P inverse AP equal to D. A is the given matrix, P is the model matrix, that is we have eigenvectors x1, x2, x3. P inverse, we can simply to calculate P inverse. You know, in previous methods, P inverse is adjointed matrix by det of the given matrix. Suppose P inverse equal to, we can also find P inverse equal to adjointed of P by det of P using the in previous methods. Okay, simply we have to calculate P inverse. So P inverse into AP equal to D, that is the diagonalization of the procedure. Okay, so finally D equal to lambda 1, lambda 2, lambda 1 0 0 0 0, lambda 2 0 0 0, lambda 3. The lambda 1, lambda 2, lambda 3 are the eigenvalues of the given matrix A. Okay, here lambda 1, lambda 2, lambda 3 are eigenvalues of the matrix A. x1, x2, x3 are eigenvectors of the matrix A. So this is the diagonalization procedure, P inverse AP equal to D. Okay, that's it. Next, some more definitions. Model and spectral matrices. Model matrix and spectral matrices. You know diagonalization form, P inverse AP equal to D. So here P is the model matrix and D is the D is the spectral matrices. Okay, that is the matrix P which diagonalize capital A is called the model matrix of A, and a resulting diagonal matrix, a resulting diagonal matrix D is known as the spectral matrix of A. Okay, so here D is the spectral matrices and P is the model matrices. P is the matrix P, the model matrix P is non-singular. That's why we can find inverse of the matrix also. It is a non-singular matrices. Okay, you just remember that P is non-singular matrix. That's why we find P inverse of the matrix. Okay, and some more important points are there. Okay, like just to look at it. First one is the diagonal matrix D has the eigenvalues of A as its diagonal elements. Okay, already I know the matrix in diagonal matrix D, lambda 1, lambda 2, lambda 3 are the eigenvalues of the given matrix. That is, the diagonal matrix D has the eigenvalues as its diagonal elements like lambda 1, lambda 2, lambda 3. And the second one is the matrix P which diagonalize A constitutes the eigenvectors of A. So, the matrix P having, already I told that P, diagonal matrix, P is x1, x2, x3 like this. x1, x2, x3 are the eigenvectors of A. Okay, the matrix P which diagonalize A constitutes the eigenvectors of A. Okay, and the third one is, if the matrix B is similar to the matrix A, then B has the same eigenvalues of A. In case B is a matrix similar to the matrix A, then B's also have the same eigenvalues. If A is a matrix having eigenvalues like 2, 3, 6, B is also another matrix similar to A, that then B having the same eigenvalues like 2, 3, 6. For example, we say that, okay. So, B is a similar to the matrix A, then B have the same eigenvalues 2, 3, 6 like this, okay. And next one is, if X is a capital X is an eigenvector of A, then Y equal to P inverse X is an eigenvector of B corresponding to the same eigenvalues. X is a eigenvector of A. In case X is a eigenvector, then Y is the transformation. Y is equal to P inverse. P is the model matrix. We can it is a non-singular matrix. Then we can also find P inverse. Y equal to P inverse X is a eigenvector. Y equal to P inverse X is eigenvector of B corresponding to the same eigenvalues. Already I told that B is similar to the matrix A and B have the same eigenvalues. It is also, in case if capital X is the eigenvector of the matrix A, then B have the eigenvector, that is P inverse X. P inverse X is the eigenvector of the matrix B, that is. And next one is, if the eigenvalues of A are all distinct values, then it has n linearly independent eigenvectors and so it is diagonalizable. In case A have the all distinct roots, that is distinct eigenvalues, it has n linearly independent eigenvectors and it is a diagonalizable. Okay, and the last one is, suppose it is most important, suppose capital A is a real symmetric matrix. Capital A is a real symmetric matrix with n pairwise distinct eigenvalues. N means that is a pairwise eigenvalues, that is lambda 1, lambda 2 and so on, like lambda 3 and so on, like this lambda n. Then the corresponding eigenvectors are capital X1, X2, Xn are pairwise orthogonal. Pairwise orthogonal means the product of the any two eigenvectors are 0. That is the pairwise orthogonal. Here A is a real symmetric matrix. We note that A is a real symmetric matrix. X1, X2, Xn are pairwise orthogonal. That is, we see that X1 transpose into X2 equal to 0 x2 transpose into x3 equal to 0 and x3 transpose into x4 equal to 0, like this. Okay, any two product of the any two eigenvectors are equal to 0. That is the pairwise orthogonal. In case the vectors are pairwise orthogonal, then we can write the model matrix P. P is given by, we can write E1, E2, E3 and so on, En. Here E1 equal to x1 by norm of x1, comma, E2 equal to eigenvector x2 by norm of x2, E3 equal to x3 by norm of x3, like this. That is the E1, E2, E3 and so on up to En. Okay. E1, E2, E3 also pairwise orthogonal. That means the multiplication of any two vectors E1, E2, Ei into Ej equal to 0. That is the pairwise orthogonal. Then that is here norm of x means that is norm of capital X. Okay. That is, we can write here also norm of x is, suppose x is a let us take any example. X is a eigenvector a, b, c. Then norm of x equal to, we can write square root of a square plus b square plus c square. Okay. That is the norm of x. Okay, we can write. So here we can calculate E1, E2, E3 like this. Okay. So it is also pairwise orthogonal. Then P is an orthogonal matrix. Then definitely pairwise orthogonal means P is also orthogonal matrix. We know that orthogonal matrix, the property of the orthogonal matrix is, that is P inverse into P equal to P into P inverse equal to I. Okay, we can also write P inverse equal to P transpose. Okay, we can write P inverse equal to P transpose. Both are equal. P inverse and P transpose matrix are equal when P is orthogonal matrix. Okay, so we conclude that generally the diagonalization process is P inverse AP equal to D. That is the diagonalization process. In case if A is a real symmetric matrix, we can substitute P inverse by P transpose. So if A is a real symmetric matrix, we can also write P transpose AP equal to D. Okay, this is also diagonalization method. Okay, so we cannot find no need to find P inverse when A is a real symmetric matrix. Okay, so you can find eigenvalues and eigenvectors and write the model matrix P equal to x1, x2, x3, and they are directly to take P transpose only, P transpose, and multiplying P transpose AP equal to, we have diagonal matrices, that is diagonal of lambda 1, lambda 2 and so on, lambda n. That is the diagonal. So diagonalization process is over. Okay, that is whenever A is a real symmetric matrix, definitely P is orthogonal matrix. We can also write P inverse by P transpose. So P transpose AP equal to D. That is also, we can prove that diagonalization method. Okay, that is the one point. Okay, important point. Okay, and we can also find some powers of the matrix also by using diagonalization method. So here you see that let A be a square matrix, then a non-singular matrix can be found such that D equal to P inverse AP. So D equal to P inverse AP is a diagonalization method. Okay, so in this form D equal to P inverse AP, we can write PD into P inverse equal to 8 also. PD into P inverse equal to A. Okay, I will explain. So here, just write D equal to P inverse AP. Okay, same. Multiplying P on multiplying the matrix P on the both side on left side. Okay, so we can write PD P into P inverse AP. So we can write the above form is P into P inverse into AP. So we know that P into P inverse equal to I. Okay. So I into AP, that equal to I is the identity matrix. PD equal to AP. Again we can also multiply P inverse on both side on the right side of the terms. Okay, both side. Okay, P inverse. We can write PD P inverse equal to AP into P inverse. So we can also write A into P into P inverse. P into P inverse is I. I into A is A. Therefore A equal to. So PD P inverse equal to A. That is, we can write. First of all, D equal to P inverse AP. This procedure we can also write A equal to PD P inverse. So now find the power of the matrix. In case A equal to, that is 1. A equal to PD P inverse. D is a diagonal, P is a model matrix. P inverse is the P inverse of the matrix P. Okay, now find A. So now we have to calculate A square. A square equal to A is a PD P inverse. A square equal to A into A. So same thing like this, we can write PD P inverse into PD P inverse. Okay. So this can be written as here PD into P inverse into P, D into P inverse. Okay. Here P inverse into P is identity matrix I. I into anything matrix, same matrix itself. Okay. That is PD D into P inverse. So D into D, D square. Same P into D square into P inverse. That's why A square equal to same P into D square into P inverse. So similarly A cube also we can write A square into A. A square is already we know A square is P into D square into P inverse. A is PD P inverse. So by using the above process, same thing like this, P into P inverse is I. So we can also write P into D square into D is D cube into P inverse. Okay, like this ways we can write A cube, A power 4, A power 5 also. So finally, in generally we can write A power n. A power n is any positive integer. That is the power of the matrix. A power n equal to P into D power n into P inverse. D power n is the power of the diagonal matrix. So we can write also P into diagonal matrix are lambda 1 power n, 0, 0 and so on, 0. Next lambda 2 power n, 0 and so on, like this. Finally last term is lambda power n all power n into P inverse. That is the matrix. So we can use diagonalization method. We can find also power of the matrix also. Okay, that is the power of a matrix. By using diagonalization, we can take any A cube, A power 4, A power n also. N is any positive integer. So this is the basic definitions of the and procedure of the diagonalization method. Okay. So next, so these are the definitions. Next we have to discuss the problems of the diagonalization. Okay. So This is the definite, we have take the references. So next class continues. We will discuss the problems of the diagonalization. Okay. Thank you.